Recently, I've been playing around and taking a deep dive into Linux. Right now, I'm actually reading this book, How Linux Works by Brian Ward. Now, as I've gone through some of this reading, I've stumbled upon an interesting technology called eBPF, or the Extended Berkeley Packet Filtering Software or program. It's a virtualization technology that exists within the Linux kernel. Overall, what eBPF does is it allows users or a program to execute custom bytecode within the Linux kernel without having to load in an extra kernel module or modify the kernel source code. eBPF can be used for a multitude of reasons, and if you're on this channel, you're probably wondering, it's probably have to do something with security. In this case, eBPF can be used for isolated security analysis to detect malicious operations. So we'll get to all this here in a moment. In today's video, I will be overviewing from a high level the architecture of Linux, what eBPF is, how it works, and I'm going to show you a malicious or detection operation using a sample environment in today's video. So we have a lot to cover. Let's get started first by looking at just basic Linux architecture. Linux can be divided into two distinct spaces, the kernel space and user space. Kernel space is where the core of the operating system resides. It has full unrestricted access to all hardware, including memory, storage, CPU, and much more. Kernel space only runs the most trusted code. Now, user space, on the other hand, is where anything else that is not kernel process runs, such as I/O, file system manipulation, running applications, and these programs have limited access to hardware. To communicate between user and kernel space, an API is exposed to the kernel. User space programs send system call functions to the kernel. These system calls, often abbreviated as syscalls, provide many different functionalities, including process control, file management, and device management. Syscall are usually implemented in the language C, mixed in with some assembly. While system call interface provides a layer of abstraction of privileged and non-privileged control, developers needed more flexibility to add support for new hardware, file systems, network protocols, and more. Linux kernel modules, or LKMs, were developed for custom programs to access hardware directly without adding to kernel source code. Unlike syscalls, where requests travel from user to kernel space, LKMs are loaded directly in the kernel at runtime, making them a part of it. As helpful as LKMs are, they introduce a lot of risk to the system. The division between user and kernel space allows for a number of security measures to be bypassed by LKMs. The industry has turned to other solutions such as eBPF, which is embedded right inside the Linux kernel. eBPF is an extended version, as the name suggests, to the classic Berkeley packet filtering software. This was an observability program which was primarily used to analyze and observe network packets. Okay, so let's take a look inside how eBPF works. In my opinion, if there's one thing to remember about this video and this topic is that eBPF is an isolated virtualization technology that exists within the Linux kernel. You don't have to modify Linux source code. You don't have to add in extra modules. It all exists within the Linux kernel. From a very high level, eBPF programs are event-driven and are run when the kernel or application passes a certain hook point. A hook is like a detour. Predefined hooks such as system calls or network events provide eBPF the ability to insert or attach itself. Before being attached to the request hook, eBPF must pass a series of verification steps. These verification steps ensure the program does not crash, harm the system, and always runs to completion. Next, a just-in-time or JIT compilation step translates the generic bytecode of a program into machine-specific instructions. This makes eBPF programs run as efficiently as natively compiled kernel code or Linux kernel modules. There are also helper functions and maps. Helper functions are well-known and stable API which allow eBPF programs to make function calls. Now, eBPF cannot call into the arbitrary kernel functions, so helper calls can be used to manipulate these network packets, get process context, get the current time and date, and much more. Maps are used to store and retrieve data. eBPF programs can share this collected information. What's the security implications behind eBPF? From a security perspective, what does eBPF do, really? Well, in order to detect suspicious or malicious activity, there are certain telemetry that you need to collect, and the more information, the merrier. Telemetry collects a wide array of information, including what system calls are happening, the processes running, how systems are behaving, maybe process starting events, network connections, namespace changes, and much more. There are many different places in Linux to gather this information, and the ideal place is in the Linux kernel. Now, traditionally, this was done with the Linux kernel module, among other technologies. And well, now eBPF can be used to run and analyze these events in an isolated virtual machine within the kernel without having to add an extra module. This allows the tools to modify packets, change syscall arguments, modify user space applications, and analyze for malicious behaviors. And this is the real security power of eBPF. Let's see eBPF in action and simulate a malicious technique or behavior used by attackers. Now, in today's video, I'm going to be using Teleport as my environment. Teleport is an open source project which allows you to manage your SSH connections among many other different use cases. You can see my video, I'll link in the cards here or in the description below, of the Passwordless Home Lab crash course that I recently created with Teleport. It's completely free, open source. Here in front of me, I have a Teleport cluster. And this Teleport cluster, basically all it's doing is managing all of my SSH connections. Now, as part of this Teleport cluster, there is an audit log, and I was just on it. And you can see that you have all of these different commands going on, certificates issued. There's all different types of behaviors and events that are logged here. Right now, I have one SSH node connected to this cluster. In this case, it's an AWS EC2 virtual machine. There's nothing on it. It's just a Linux machine. And in this case, I have two SSH connections. So this one is showing the Teleport daemon, or the agent that's running on this Linux virtual machine. And here is another one. So if we go ahead and clear my screen, you're going to just, see just a regular Linux machine. Using eBPF, Teleport in this case is able to take unstructured SSH connections and commands and put together a particular context into really seeing what's going on in the environment. Now, like I said, there are several ways that you can do this, and eBPF is just one of them. Let's take this command that I already have pasted into my environment here. A common technique used by attackers is to obfuscate their code with base64 encoding. An attacker could use this to, let's say, exfiltrate some information, evade detections, or maybe communicate with a command and control server. So hitting enter, you can see that this is just a basic curl command, and it's going to the example.com domain. Now, if we go to our Teleport cluster and we go to the audit log, we're going to see a few things. Session commands have been logged, and in this case, you're going to see sh, base64, and the curl command all logged together. You can get more details if you wanted to. And it's able to understand what's going on, or where it was going. So in this case, just example.com. What's going on behind the scenes? Specifically in this case, TCP Connect programs are used by Teleport. TCP Connect program traces TCP connections, and TCP Connect is used and traces with the connect syscall, which initiates a connection to a particular network socket. When the program is triggered along a code path, which is a set of instructions, TCP Connect will start outputting information. All of this data has been collected using helper functions, as mentioned before. TCP Connect is a part of BCC, and BCC lives out on GitHub, among other areas. And basically, it's an eBPF helper function or wrapper that allows you to write eBPF functions and capabilities inside, say, Python or much more user-friendly language. Now, in this case, as you can see, I have TCP Connect's Python file from BCC up here. The reason I'm showing you this is, of course, you don't have to write all of these helper functions or look at eBPF. This is just the beginning of eBPF, and if you're like me, this stuff can be really confusing. eBPF is a cool technology and probably something you'll see implemented, if not already implemented, in future agents and technologies such as antivirus agents, EDR, XDR, among other sensors that are installed within Linux boxes. I'll leave some reading in the description below for further analysis if you're interested in this topic. And well, yes, until the next time, have a good day.